In this section, we're going to learn about OSPF version 2 for IPv4. To form an OSPF peering between routers, first OSPF must be enabled on routed interfaces on a common subnet between routers. Then hello packets are used as discovery messages between the routers sent to multicast address 224.0.0.5. Inside the first hello packet contains the local and remote router ID values for each OSPF router. Router IDs are local router values that are used to identify routers, and they must be unique in an OSPF topology. There are three ways that an OSPF router can receive a router ID. First, we can manually configure the router ID under the OSPF process. If there is not a manually configured router ID, then the router will choose the highest loopback IP address, and then if no loopback interfaces exist on the router, then it'll just use the highest interface IP address for its router ID. Once a router responds with a hello message containing its router ID information, then OSPF has reached the INIT state. After the third hello in the exchange between the routers, if the OSPF neighbor adjacency requirements are met, then the routers reach the two-way state. Then, routers send database description information at the XStart state, exchange state, then go to the loading state where they send link state updates, and then finally, OSPF routers reach the full state, become OSPF peers, and send routing information between each other. To build an OSPF topology, link state advertisements are sent between the OSPF routers to build link state databases. Once the link state database is filled with routing information, then the Dijkstra SPF algorithm is used to process the link state database information to build the routing table. Once the SPF algorithm runs, then the link state database information can become routes in the routing table. Since the SPF algorithm can be a lot of work on a router, to scale OSPF, areas are used. Areas are basically link state database boundaries between OSPF routers. So then you can split up the load of running the SPF algorithm. And this can help scale OSPF topologies because once you get into hundreds of routers, that's a lot of memory and processing overhead for OSPF routers. So really, in a smaller topology, you can get by with a single area because it's not that much work for the router to run the SPF algorithm. But once you get into a large amount of routers, then you want to start splitting up your link state database boundaries with areas so that the routers don't have to do as much work. With OSPF areas, there's always a backbone area, which is area 0. And this is the main area in OSPF. So if you're only going to have one area because you have a smaller topology, then the one area you would use would be area 0. And this is always going to be the first area you create. Then once you start scaling your topology, you start creating non-backbone areas, which are any area that's not 0. As you scale your topology and add more non-area 0 areas, one key thing to know is that non-area 0 areas have to be connected to area 0. If they're not connected to area 0, then you're not going to have a supported OSPF topology, and the OSPF routing information is not going to be propagated as you'd expect. So just always have area 0 be the core of your OSPF topology, with all non-area 0 areas connecting to the backbone. Another important concept to understand with OSPF is designated routers. Designated routers handle database exchange information between routers on each subnet. Routers use the link local multicast address 224.0.0.6 to send database exchange information up to the designated router. And this prevents all the routers having to send the same information to each other. Instead, they can send it to the central point in the subnet, which would be the designated router. In addition to designated routers, you can have backup designated routers. And these take over the DR role if the DR were to fail. To elect a designated router, there's an election process. First, routers look at which router in the topology has the highest priority, and that would become the DR. The router with the second highest priority would become the BDR. If the priority values are the same, the tiebreaker is the highest router ID. And then the second highest router ID, again, would be the BDR. Both the interface OSPF priority and router IDs can be configurable, which you'll see in our configuration example section. Any router that is not a DR or BDR router is a Drother router. One important thing to know about Drother routers is that when they do form OSPF peerings, they're only going to get to the two-way state. And that's because since they're sending their database information up to the DR, they have no reason to exchange database information to get to the XStart, exchange, or loading states. OSPF uses cost as its metric value. So just like RIP version 2 used hop counts to determine which path was the better routed path, OSPF uses cost. And this is going to be added up for each outgoing interface for the path to the route. Kind of like how Spanning Tree uses cost to determine its best path to the root switch. So let's take a look at an example of how OSPF routers use cost to determine the best path. If R3 advertised its 10.3.0.0 network to R1 via its path directly to R3, or from R2, it would add up the cost of the outgoing interfaces for each path. If we go from R1 to R2 to get to the 10.3 network, we have a cost of 3. Because the 3 outgoing interfaces in that path each have a cost of 1, equaling 3. The route from R1 directly to R3 for the 10.3 network is a cost of 2, since we have 2 outgoing interfaces and they both have costs of 1. And that would be the more preferred route since it has the lower cost value. Cost is derived from the actual bandwidth of the routed interface. This is called the autocost reference bandwidth formula. So OSPF routers by default have a reference bandwidth of 100 megabits per second. And the formula is you just take your reference bandwidth, whatever that may be, and then divide it by the actual interface bandwidth. Since our actual routed interfaces were 100 megabits per second, which is the same as the reference bandwidth, 100 divided by 100 is 1, giving us a cost of 1. The reference bandwidth value is of course configurable, and you want to make sure that if you have 10 gig links and 1 gig links that you adjust your reference bandwidth to be the highest possible bandwidth in your network. Hellos are used as keep alives and are sent every 10 seconds by default between OSPF neighbors. If a link were to go down in an OSPF topology, if a hello is not received before the dead timer expires, so after 40 seconds by default, then the routers would consider that neighbor to be down. And that's how an OSPF topology knows if a routed path is up or down. The default OSPF administrative distance is 110. So if we look at an example, if R3 learned the 10.12.00 route from both R1 and R2, it would choose the best path based on administrative distance. In this example, since EIGRP has the lower administrative distance when compared to OSPF's 110, then unfortunately for OSPF, the EIGRP route would be preferred. One key thing to know with OSPF is how you advertise default routes. To advertise a default route from a OSPF router, you simply use the default information originate command underneath the OSPF process configuration.